Yeah. Hello, everyone. It's our pleasure today to have Antonio to share about his work with us. Like today, he's going to kind of talk about how dissipation can be used as a resources for quantum reservoir computing. I think this is pretty cool because finally we have some kind of good numerical work to show us the practicality of quantum reservoir computing. And today's Antonio will be able to tell us more about this. Antonio, the floor is yours.
So thank you. So thank you for inviting me. It's a pleasure. And so the idea of this talk is to show the result of our last publication. And I want to show how we can use dissipation as a useful tool to improve the performances of quantum server computers. But I want to start from the beginning. So I want to start from the general theory of also classical server computing to finally show the more technical results of our work. So going so reservoir computing is a supervised machine learning method that is suited for time series processing. We can, in general, think about server computing with this scheme over here. I don't know if you can see my point. So maybe yeah.
Yes,
Okay.
we can see.
So
Yeah, good.
okay, good. So server computing can be summarized with this scheme. We have an input, that is the time series that we want to study. We have a substrate, is the reservoir that will evolve according to the density that we want to study. And then we can extract from the substrate some information about the time series, and we can tune this output in order to solve the task in which we are interested. So going more specifically, as I say, the input is a time series, and I will indicate its value during this talk with SK. And an example of task that we can think about solving with quantum server computing are, for example, forecasting aquatic dynamics, and I will show later a task that we also used for our work about that. And another possible thing that we can do is, for example, analyzing another time series in order to, for example, translate a vocal message to a text. So we have to extract the information about which are the words that are presented in a vocal message, and then we can put it in a text. Now we go to the substrate. It is what we call reservoir. And in the most general case, reservoir is a dynamical system. So we have a dynamical system whose state I indicate here with xk, and it is evolving according to the values of the time series that we are studying. Interestingly, this dynamical system can be digitally implemented, and in fact, the first proposals of server computing have been neural networks, so thought to be implemented on a digital computer. But interestingly, this formalism can also be applied to physical systems. So we don't need to have a digital computer, but we can have physical systems. And this is the case that we are studying now, because in our case, our reservoir is a quantum system. So it's interesting that you can apply this formalism even in these cases. So now going to the output. At each time step, the output that we will extract is a linear combination in general of observables that we can measure from the reservoir. The fact that we are using a linear combination allow us to avoid a typical problem that it is present in recurrent neural network, which is the vanishing gradient. The fact that we have just a linear combination allow us to have a very cheap training that does not present these kind of problems. Actually, of course, these weights of this linear combination have to be optimized accordingly to the task that you want to solve. So, as I said, it's a supervised machine learning method, and so we train these linear weights. And another important thing is that this is the only thing that we train. So the reservoir, we will need to train the reservoir. And due to that, we can say that our reservoir computing is multitasking in the sense that we can use the same dynamical system to solve different kind of tasks. We're just to train the linear weights. Say that, I can now switch to the quantum case. And in the quantum case now, the state of the reservoir is xk, is more generally is the density matrix of the system. And the first proposal of quantum reservoir computing was like a transient field leasing model in which we have this Hamiltonian here, in which all the spins are like fully connected and the couplings have been randomly. So it's like a disordered network, we can say. And we have also an orthogonal magnetic field. So now following the previous scheme, the input is injected, like, so the value of the time series that we assume here to be monodimensional is injected, preparing the state of one of the spins of the network. And following this rule here, so if I also assuming that we are rescaling the value of this time series to be in the interval 0, 1 in order to have like a normalization condition here. So we prepare the state of one spin following this rule. So like adjusting the weights of the linear combination. So this like following like this state value. And then we let the system evolve accordingly to its Hamiltonian. I want to stress the fact that I will like also underline it later, that the preparation of one spin of the network is a non-unitary operation. And it is a necessary thing that has to be present in the updating rule of a circuit. So we need that the whole like evolution of the reservoir is non-unitary. Like after this, like unitary evolution that is now the role of this unitary evolution is to let the information of the time series spread into the other spins. So to like goes from one spin to all the others. So this is the role of this unitary evolution. And after that, we measure some observable that we choose from, which just from the beginning. So and we take the linear combination. In the ideal case, we can consider like a infinite number of measurements that can be used to like to consider like a linear combination of expectation values. Now, the motivation of making it quantum are like the fact that the number of degrees of freedom that we can extract from the system increase exponentially. So it can be like this is a window that we can use for finding a quantum speed. And also we can implement typically the fact that we don't need to tune the reservoir makes this method typically noise proof, I would say, because even if we have like experimental defects on the platform, we know that we can still train the linear way to solve the task that you want to do, and we don't have a we need like less experimental precision than other strategies, for example. And also, we know that experimental papers that like implement like practically this protocols of quantum reservoir computing have been published. So we have some examples. And another motivation is that we can use quantum reservoir computing to process time series that are quantum data. And we don't need to do a full state tomography of the quantum states. We can let the reservoir process that. So
can I ask a question?
Yeah, sure.
So you say that you claim that you have some advantage over.
I don't know. Yeah.
Because you have some resilience to noise, inherent resilience to noise in some sense.
No. Yeah. I mean, I'm not feeling an advantage because, like, I know that, I mean, there are formal theorems that ensure that if you have, I mean, the more degrees of freedom that you have of a reservoir, the better the performances. But in this quantum case, we're not sure if all this, like, expectation, but all these components of the linear combination are really linearly independent if we have a finite.
Are really what? Sorry, I cannot.
If we have a finite number of measurements, we are not sure if the number of outputs that you are taking are really linear independent. So it's like having a finite number of measurements can reduce the performances, and yeah. So
what I meant is that do you have any formal or half a formal proof that doing non-unitary operations, like the state preparation that you have, really helps you to fight noise, which you wouldn't have been able to do otherwise if you were doing only unitary evolution? I mean, I think that's the intuition you have there, right?
I mean, I'm not quite much to things because every non-unitary stuff, we have formal rules that ensure us that if we have non-unitary element, we have fading memory, right? And we know that if we work on this regime, the more degrees of freedom we have, the better will be the performance in solving time series tasks. About the noise, I'm just saying that if we have an experimental platform in which we don't have so much freedom about choosing, for example, these random weights, we can still train the reservoir. We don't have to train these couplings.
Okay. All right. Okay.
Yeah. I was talking about this kind. Yeah.
Okay.
And
thanks.
Yeah, sorry, I do have another question over here. So you mentioned the motivation is that the number of degree of freedom is exponentially increased, right? So like how do you control this this exponentially large degree of freedoms though? Like what is the means of control this degree of freedoms?
The fact is that we can, for example, having like I can say if we have a certain number of spins, we know that we can find a certain number of linear independent observables that we can measure. And in order to have the same number observable in a classical system, we need an exponentially larger system. This way. This is what I meant.
I see. Okay. Yeah, thanks.
Okay. So I want now to stress the fact that we are also talking now about the non-unitariness of the evolution, and we need to have a non-unitary operating rule in order to erase the information about past inputs over time. Because of course, not all the dynamical systems can be good observers. We need dynamical systems that have some constraints in order to be useful. And the constraints that they have to fulfill are these two. One is the acostate property, which means that the reservoir state forgets its initial condition over time. So the final state of a reservoir after we inject the value of the auxiliary will not depend on the initial condition. So this is one. And we need non-unitariness for reaching that. Because we want that, for example, if we have two initial states that are, for example, two different density metrics, we want that these two density metrics will converge to the same after injecting the same inputs. But if my evolution is unitary, this distance will be always the same over time, and I cannot have this property. And now, consequence of acostate property under typically fulfilled continuous condition is the fading memory property, which means that the state of the reservoir will depend only on the recent input injection. So we forget about the past input injection. I hope you will recognize the reference. I say that, like I said, the previous example, the non-unitariness is introduced by the partial trace. And this partial trace is a discrete operation. And in this work, what we did is to consider continuous way for controlling this information ratio. And for doing that, we introduced the physics of open quantum systems. So we worked under the Markovian hypothesis. So we consider that the correlation time that is physically can be physically justified if the path correlation time scale is negligible in comparison to the system evolution time scale. So under this regime, we know that the evolution of my quantum system is Markovian, and it means that updating rule of my reservoir will not explicitly depends on the previous states of the system. So under this condition, we know that we can describe in a very general framework the evolution of the system that we now consider that is interactive with an external environment with the linear master equation. And going now analyzing terms, we know that now the evolution is generated not by the Hamiltonian but by a Liouvillean, which is a non-Hermitian superoperator. And in our case, we know that we want to have a dynamical system that will depend on the input. So we will consider this Liouvillean to be a function of the input that we want to inject the reservoir. So it will depend on the time series that we are analyzing. And also this Liouvillean action can be, is composed by these two terms. One is the Hamiltonian term that is like the system Hamiltonian. And then we have another term that depends on, that describes the interaction that our system has with the external environment. And we have this jumps operator that describes how the environment is acting on the system. And then we have these damping rates that we can think that are like a measure of how strong the environment is acting on the system. So in comparison to its Hamiltonian evolution. And we will use these terms to tune the information ratios. So going now to our proposal, our model proposal, as I said, now our system is a Markovian reservoir. We have these application rules that will depend on the like input dependent Liouvillean, and where like this delta T here is the input injection. So the time that the time in which the system is interacting with external environment at each time step. Then we change it the way in which we inject the input, because before the input was injecting, like preparing the state of one spin, but now in this case we are injecting the input by tuning the magnetic field of this Hamiltonian. So we have the same Hamiltonian as before, but I introduce another magnetic field that is now input dependent discretely, as I can, like, as you can see from this this scheme here. And now I want to show also the environment action, and I consider to have n jump operators when n is the number of spins that are this sigma minus like that have this sigma minus matrix. That means that they are, I can say that are pushing the spin to be down, I could say. And I consider the easiest case in which the loss, like the damping rates are uniform over the network. So all these spins are affected with the same strengths by the external. Now, the motivation about this model proposal is that we know experimental way to implement this kind of dissipation. So these minus terms that can have this effect. And also the quantity that we are introducing now, we found with our numeric, this gamma here, this strength of the interaction, this strength about the interaction with the environment is useful modeling parameter, and also we show in the version of Perfect 2D. And also now the information is injected and erased over all the spin networks. So we think that, like heuristically, that in this way we can have like a way to inject the information and to erase the information that like depends less on the system sides, because we are always acting on all the spins. Say that, I want to show to you how we tested our model, and also how we compared our model of dissipation with the discrete one. And the first task that I'm showing you now are these memory tasks that are tasks used to see how a reservoir is able to linearly and non-linearly process a set of previous inputs. And we quantify the performance with this capacity here, where this y here is the target time series that we want to reproduce, and this y with a bar over there with this half is like the time series that our reservoir are predicting. And a capacity equal to 1 means that we reach the perfect prediction, and a capacity equal to 0 means that we don't have any correlation with the target that we want to reproduce. Now, the first task that we study is the short-term memory task. And so we consider the input to be uniformly extracted from the interval 0, 1. And the reservoir has to remember which was the input up to a certain delay. So it's completely linear. We are not like asking to compute the product of some input. It's just like saying which was the input. And as we found in our numerics, we can see that our model is able to outperform the other one in which information is erased discretely. And we can see that it holds for various values of delays. And for the delays that we explored, seeing that we can have a better linear network. And we consider here a system of 5 spins. Now, in order to introduce some nonlinearity, I consider to study the normal task, in which we have like a quadratic term now in the target series, that is this term here. And this is a nonlinear task, but it's not so, the degree of nonlinearity is still not so strong. Just a quadratic term is here. And in order to study now a task that is strongly nonlinear, we consider this buddy check, in which now the input is uniformly extracted from the interval 0, 1, in which it's a binary input. And what you want to be able to do is to compute the parity of the bit string we can form considering the set of inputs that we have injected. And as we can find here from the value of the capacity, also for both value of the delays, even for the normal task and for the function task, the value of the capacity that we can reach with our model are higher. Proving that numerically, like that in this case, having like hyperparameter that can be used for tuning how much information are you erasing from your system can be helpful for improving the performance. So I think maybe there is a question. See, open microphone. Is there a question? No. Okay.
Sorry?
I think someone opened the microphone. I don't know if.
Oh, no.
Question?
I think.
Okay.
Yeah.
Okay. Okay. So now we also consider a different like task. A different kind of task. It is, like I said, the forecasting of a chaotic time series. And in this case, the time series that we consider to forecast is the Mackey-Glass equation. It's a typical series that is used to test systems of the several computing systems. And it is like it's a chaotic time series. It's the solution of a delayed differential equation in which if our delay is big enough, this solution is chaotic. And in our case, we tested the capability of the reservoirs to be able to forecast the value of this solution. And we consider this framework. So we train the reservoir to be able to pick the one step ahead like value of the time series. So the training consists on having a value of the Mackey-Glass time series, and the reservoir has to be able to predict the next one. So we train the reservoir with the numerical solution of the differential equation. And then in the test phase, we consider that the reservoirs have to be autonomously evolved following like the prediction that they are doing. So the reservoirs, they don't have any knowledge about what is the real solution of this question, but they put their prediction as the input of the next step. So they are following their same predictions going ahead in the future. And we use this like this framework to test the differences between our continuous distribution model with the discrete one. And the first thing we did is to see if the models are able to be able to reproduce the shape of the cortical attractor, typical cortical attractor of the series, and we found that they both relatively can be able to be chaotic and to produce the attractor. But if we go more into details about the reproduction of the trajectory, we can see that our model, I mean, even quantifying it with the mean square error, we can see that our model is able to have a better mean square error, and also cumulatively from this picture, we can see that it's able to better reproduce the oscillation of the numerical solution of this series autonomously, as I say. Okay, so as we can see, both from the memory task in which we asked the servers to process previous inputs, and also from this series forecasting, we found better results using our model. So, do you have any question?
Yeah, I have a question over here. So on this like graph at the lower right, when you kind of like do the predictions, like do you know why the FN model has larger standard deviation compared to the CD model? Like after the prediction.
I see it is a matter of the best parameter that we found, probably, because we have the it's a possible explanation. Now, the fact that maybe if we found if we found that the system is able to work with okay, we have this magnetic going to the Hamiltonian, we have this magnetic field here, and we have these couplings here. So if the best hyperparameters of the model can be able to solve the task have a lower magnetic field, means that now these couplings can be more relevant. So, and this like standard deviation is a standard deviation that computed considering this random randomization of the. So I think that this is why it's bigger, because they are more couples.
I see.
Yeah. Okay. So now another important point is, like I mentioned before, is the role of measurements. Because we know that the performance of a quantum reservoir computer can be like strictly depends on the number of measurements that we have available for estimating the output layer of servers. Because in the real case, with our number of measurements is finite, so our output layer is not composed by real expectation values, but is composed by an average of a finite number of shoots. So these effects of shoot noise can decrease the performances of our computer servers. And the answer work, the work that I'm showing now, I'm showing is like study these problems. And we also wanted to see what happens if we apply this show noise effect in our case for our comparison. And we implemented the show noise effect, considering like that our output layer is composed by like a value that is extracted from a constant distribution, whose means is the real value of the surroundings, and whose standard deviation is 1 over square root of the number of sample available. And what we can see from this plot is that the less measurement we have, the worse will be the performance. And in order also to find an advantage with the dissipation that we are introducing, we need to have enough measurements to be able to really see the advantage. And this is like a property that is like specific of this model. But what is general is that the less measurement we have, the worse will be the performance. So we found that the rules in which like the performance increase with our model in comparison to the discrete model needs like allows us to conclude that we need enough measurements to have an advantage with this continuous measures. And in this case, we consider to test the effects of this high number of measurement with the shorter memory task. So the linear task, we took this linear task to test this property. And we consider here two kinds of delays. So a delay equal to 2 and a delay equal to 10. And we see that, I said, we need enough measurements to see the advantage given by dissipation. So now I want to go to a more formal result that we had. And I want to talk about universality. And in the literature of reservoir computing, with universality, we mean the possibility of a set of reservoir to be able, in principle, to approximate any faded memory map. And in order to be able to reach universality, we need a class of reservoirs that can, in principle, be able to discriminate two different time series, no matter how close they are. But we need to be able to say that if two time series are different, from the class of the reservoir that are universal, we need to find two reservoirs that give two different inputs. So like you can see here, we can have, even in the extreme case of two identically equal time series, but only one point is different, we need a reservoir that's able to discriminate it. And we formally proved in which condition Markovian quantum reservoir computer is universal. And we found these conditions here that Julian has to fulfill. And as I said, now the dynamics of our quantum reservoir is generated by an input-dependent Julian. And if this input-dependent Julian respect this free property, so if the stationary state of this Julian is unique, if the Julian is a continuous function of the input, and if for different inputs the corresponding stationary states are different, we know that we can find a class of reservoirs that evolves according to this Julian that are universal. And the main idea of the proof is that we can, the fact that the stationary states depend on the input and it's different for different inputs, no matter how close they are, this property allows us to discriminate two different time series. So we can use the stationary state as a tool to separate different series. This is like the proof. And actually, I want also to underline that if we have a Julian that fulfills this property, can use it for, sorry, in general, I think that we can use this property as a guide to find a useful Markovian quantum reservoir. Because like typically having a universal reservoir means that you can also, I mean, typically you have also good results in the practical task in which you're not really using different reservoirs. You're not using all the class, but even taking some reservoir of this class is a useful thing to. I think it's a guide to design Markovian quantum reservoir. And also we have a work that we will publish soon in which we will follow this criteria for find quantum reservoir in our context is about spinatic, but we use a bosonic lattice, but using this this property we found a practically working reservoir. Say that, I can now conclude my talk. I want to say that like the main conclusion that we found with this paper are that tunable losses with an external environment can be useful for like tuning how much information an reservoir is erasing at each time step. And we tested it in linear tasks, So it's like this kind of tools we found it's useful in different regions, and also in forecasting in series, as I say. And we also find the necessary condition for having universal confidence intervals. And as outputs, we would like to explore more complex dissipation scenarios, like for example, exploring the non-restrictive regime, and also to consider to see the interplay between dissipation and performances, even for tasks that are not classically. So the time series that we are analyzing is not classical time series, but it's like a time series of quantum states. And say that, I want to thank you for your attention, and also to thank my collaborators here. So thank you. If
Yep.
you have any question,
Yeah, thanks, Antonio, for the very interesting talk. For the audience, if you have the questions, feel free to unmute yourself to ask the questions, or type the question in the chat, then I could help you kind of ask the questions. Maybe in the meantime, I could add some questions over here. Yeah. So when we nowadays like talk about quantum machine learning, we always like talk about like Baron-Bertolds, right? And I know like just now you mentioned that like basically you can utilize dissipations in order to mitigate Baron-Bertolds. I'm just wondering that how like whether you are using the same dissipations in proving those results, and how would that be, and what is the kind of like more like motivate, not really motivation, just like intuition behind like why dissipation could help in mitigating the Baron-Bertolds.
Okay. In the case of mitigating Baron-Bertolds, the intuition is a bit different, because here the intuition of using dissipation is more related to erase information. So it's more relating to the fact that we are using this external environment to take the information about the system, and we are tuning out this information. Now we can also erase it during the time. But in the case of Baron-Bertolds, I would say that the intuition it's more relating to the expressibility of the system, I can say. Like we can use this external environment to reduce expressibility of the system, and having a less expressive system can be used for training the Baron-Bertolds. No? It's like I'm reducing the expressiveness of a state of my system, and the environment is taking information. This is an intuitive way in which we can see it. But formally, what we found is a dissipation. If we go to the like now, I showed you the linear master equation, in which I have a library that is used to describe the evolution of a quantum state. But if we go to the Heisenberg picture, we can also considering that the observables are evolving, and using dissipation allow us to map global observables to a local one. It's an effect that you can only have momentarily. And we know that for shallow circuits, having a local cost function allows you to avoid Baron-Bertolds. But if you have a global one, typically you have it. So what we proved is that using dissipation, we can map a problem that is initially a definition of a global unitary, the definition of an unitary now is local. And so it's more like to this static stuff. It's more static non-intuition, no? Because in this case it's more dynamic, I would say. It's more dynamic.
I see. Like basically you explore two different kind of aspect of dissipations and use it for different tasks. Okay, I see.
Yeah.
But but follow on the Baron-Bertolds questions, like when you consider dissipations and then mitigate the Baron-Bertolds, right? Would this kind of system be classically simulatable? Because like recently, like Marco has the papers on like basically for those scenario where we have no bivettals, then is like most of them are classical synthetable. So I'm just wondering whether the one that you consider will fall into these cases or not. Yeah.
Yes. I think you still have classical similarity. I don't have a formal proof, but my intuition is that yes, because the information that you're relating with dissipation makes your system classically simulable. Yeah.
Right. I see. Yeah, it's just like currently, Tibarat have a questions. Like Tibarat, feel free to unmute yourself and ask a question.
Hi, can you hear me?
Yeah.
Hello?
Yep.
All right, thanks for that nice talk. So I have one question related to the universality result that you proved nicely. I'm not sure if I know what is the relationship between the universality requirement and the performance of the reservoir. Because I know there are many stuff that has been proven to be universal, but in practice, you might need an infinite number of bases. For example, Fourier basis. If you use a Fourier basis, then you need infinite number of bases to expand function. At the same time, there are some non-universal series like asymptotic series. You have finite number of terms, but you can approximate what you care about too well. So I was wondering, in your case, of course, universality is nice, and having certain conditions to show that it's universal, it's great. But what is the relationship between the resources required to approximate a good dynamical system or something like that?
As you say, it's not you can have also a system in which you don't prove universality, but maybe for the specific task that you are studying, the system is actually working. So you don't need to be able to have something that is universal for having something that's also useful. But I think that it's not like a necessary condition for solving a practical task. I agree with this. And it's like I think that if you have the good thing about universality, in my proof, what part of the proof was proving that we have acquisitive property of Feldman memory, and maybe this is actually the really important thing to say, because also I think that I didn't say here is that having a time-dependent stationary state allows you to have acquisitive property and not having I would say a trivial reservoir injecting series. Because, for example, if I have this is the most practical thing that's part of the problem. So it's like if I have like a unitary system in which my stationary state, considering unit noise, for example, in which my stationary state is each time step the identity. If I will inject times value of a time series over time, I know that I will have a cosine property, but my cosine property translates to the fact that my states over time will converge to the end. That does not depend. It's on the CS. But if my stationary state at each time depends on the input, you can avoid that.
Right. So I think that the intuition behind this eco-state properties and the fading memory is that when you have a new input, you can drive the reservoir to respond, and you forget the past at some point, so that the new input can impose certain memory on the structure of the reservoir. So if you don't forget the past at all, the new input cannot influence the system. Is that the necessary condition for the reservoir to be able to be useful?
Yeah. You have to forgetting the past, but also putting information about the present itself.
Right, and the universality here refers to the universal approximation theorem for the dynamical equations of the input, or of what?
Yeah, because here, for example, here in this case, universality means that we can formally define what is a fading memory map, which is a continuity condition under a weighted norm. And in this case, I'm saying that if I take a class of Markov reservoir and I take a fading memory map, whatever it is, like a fading memory map, example of fading memory map are these memory tasks is here. I can use I can find reservoirs, combination of outputs of reservoirs we can, in principle, being able to reproduce this spectrum. The fact is that we don't know how complicated it is to find these reservoirs and how many reservoirs we have. You know,
Okay, thank you very much. Nice result that you've proven.
You're welcome.
Yep, cool. Since like there are no other questions from the audience, so let's thank the speaker again for the very interesting talk, and hopefully we will be able to read your follow-up paper pretty soon. I guess like you'll be putting out on arXiv like this month, right?
Yeah.
Yeah.
Hopefully,
So
yes.
yeah. Okay. Yeah, I understand
actually,
how
yeah.
Mhm.
Yeah.
Sorry, go ahead.
Actually, I will underline a bit more this speak about the cost property. So yeah.
I see.
About
I see.
yeah.
Looking forward to that.
So thank you.
Okay. Yeah. Thank you.
so
Yeah.
much.
See you. Yeah. Thanks
Bye.
for
Have a good
speaking.
day.
Bye.
Thank
Yeah, you
you.
too. Enjoy your holiday.
Thank you.
Bye.
Bye.